Hi, this is Dr. Gilbert Eyabi. We are looking at section 1.4 on binary operations with the text Modern Algebra by Gilbert and Gilbert. Now, what are binary operations? We all are familiar with the operations of addition, subtraction, and multiplication. And as a matter of fact, these are examples of binary operations. When we speak of a binary operation on a set A, we have in mind a process that combines two elements of the set to produce a third element which is also in the set. A couple of things that we want to watch out for. The third element that is produced from the two elements that combined has to be unique. And secondly, it must always be possible to combine any two elements of the set, no matter which two are chosen. We would go ahead and now give you a formal definition of binary operation. Section 1.4.1, binary operation. A binary operation star on a non-empty set A is a mapping from A cross A to A. For example, define the operation star from Z cross Z to Z. Z is the set of integers by x star y equals x plus y minus 1. And that operation is supposed to hold for every x, y in Z. So what do we mean? The operation star takes two elements, x and y, and produces a third element defined by some formula which we would specify. In this case, the formula is x plus y minus 1. Now, since the sum of two integers is an integer, the product of two integers is an integer, we can see that if x is an integer, y is an integer, x plus y minus 1 would be an integer. So we can now observe that star is a binary operation on the set of integers. Now, we could be using the phrase the binary operation star on the set of integers or the set A, or in short, we could say parenthesis Z comma star to simply mean the binary operation star on the set Z. Now that we have formally defined a binary operation, given a universal set U, would the operations of union and intersection on the subsets of U be considered binary operations? I.e., if A and B are both subsets of U, if I define star as A star B equals A intersection B, does that satisfy the definition of a binary operation? What if I change the intersection to union? Would that be a binary operation? Think about that. I'll leave it as a simple exercise for serious students. The next thing we would look at under binary operations would be subsection 1.4.2, commutativity and associativity. We say that a binary operation star on a non-empty set A is commutative if x star y equals y star x for every xy in A. If I pick any xy in A and x star y equals y star x, then star is said to be commutative. When is star associative? Star is said to be associative if x star, y star z, y and z in parentheses equals x star y in parentheses star z, and that holds for every x, y, z in the non-empty set A. In other words, it doesn't matter which two of these is grouped first, the answer is still the same. If that is the case, we say the operation star on the non-empty set A is associative. I think it's time for an example. Let star be a binary operation on the set of integers z, and let it be defined as x star y equals x plus y minus 1, and we remind you that holds for every x, y in z. I want you to verify commutativity and associativity of star on the non-empty set Z. Let us start with commutativity. What do we want to verify again? We want to verify that for every x, y in Z, x star y equals y star x. As easy as that. So, for every xy in Z, x star y equals x plus y minus 1, and that equals y plus x minus 1 because x is an integer, y is an integer, negative 1 is an integer, and there is commutativity in the set of integers, and this gives us y plus x minus 1, but y plus x minus 1 is simply the definition of y star x by the definition of our operation star. So we just proved that x star y equals y star x. And in the language of binary operations, that means the operation star on the set of integers is commutative. Star as defined above. Let us verify associativity. We want to prove that for every x, y, z in the set of integers, we have that x star y star z equals x star y star z. Understanding fully well that x star y equals x plus y minus 1, and x and y are dummy variables. Very important. Okay, so we go back to associativity. We start off by putting y and z in parentheses, and that gives us x star y star z equals x star y star z by our definition of star would be y plus z minus 1. All of these is our next variable. X is a variable, and by the operation star, that gives us x plus y plus z minus 1 minus 1. And this simplifies down to x plus y plus z minus 2. And we call this equation 1. I always prefer to do it this way so we can actually see the solution very clearly. You could also just call that the left-hand side. Okay, now let's proceed to the right-hand side. We want to see what x star y in parentheses star z will give us. So, x star y in parentheses star z equals, by the definition of the operation star on the set of integers, x star y is the same as x plus y minus 1. All of that star z. All of these is a single variable right here. You could picture it as that. And we have our z. So by the definition of the operation star administered once more, that gives us x plus y minus 1 plus this z minus 1. And simplifying this, we have x plus y plus z minus 2, and we call that equation 2. Equation 1, equation 2. Some people at this point would say equal things are equal. We have just shown that the operation star on the set of integers is associative. Subsection 1.4.3 Closure. Suppose star is a binary operation on a non-empty set A. Let B be a subset of A. Then we say that B is closed with respect to the binary operation star if X star Y is an element in B for every XY in B. I.e., what we are saying is if star is a biop, which means binary operation on a non-empty set A, and B is a subset of A, B is said to be closed with respect to the operation star if for every two elements x, y in B, x star y is an element in B. That means if I pick two elements in B, any two elements, and I combine them under the operation star, and I get a third element which is also an element in B, then I conclude that B is closed under the operation star. Remember, the operation star is a binary operation on the parent set A. Examples. Example 1. Define the binary operation star on the set of integers z by x star y equals x minus y plus 2. And let the set of positive integers be our set B, which is a subset of z. Question: is the set B, the set of positive integers, closed with respect to the binary operation star? Solution: take x to be 3 and take y to be 8. Then x star y is 3 minus 8 plus 2, and the answer is negative 3, which is not an element in z plus because it is not a positive integer. What have we done? We've selected two elements in z plus that combine under the operation star, and they produce a third element which is not in z plus, and so we conclude that B equals z plus is not closed with respect to the operation star. Now, the phrase with respect to is very important. We cannot say z plus is not closed in z. No, it is with respect to that particular binary operation star that is defined on z. Now, example 2. Why don't we redefine the operation star on z as x star y equals x plus y plus 2? Now, let's still take our B to be the set of positive integers. This time around, do you think B is closed with respect to the operation star that we just redefined? I leave that as a simple exercise for serious students. Subsection 1.4.4 Identity element. Let star be a binary operation on a non-empty set A. Then we say that the element E that must belong in A is an identity element with respect to the operation star if E star X equals X star E equals X. So we can break it down in this form. E star X would be X. X star E would be X. For example, if our binary operation was just addition over the set of integers, then our identity element would be 0 because any number added to 0 is itself. For example, 5 plus 0 equals 5 equals 0 plus 5. X plus 0 equals X equals 0 plus X. If our binary operation was multiplication, then our E would be 1. And of course, in that case, our non-empty set is the set of real numbers. But why don't we define star a little differently to make it more exciting? Define the binary operation star on the set of integers by x star y equals x plus y minus 1 for every xy in Z. Question. Find the identity element E of Z with respect to star if it exists. So if I give you a binary operation that is defined, how do you go about looking for an identity element? That is what I want to show you in this part of the lecture. Now, recall that E in Z would be the identity element if X star E is X and E star X is X. I put the X in the middle so you can actually see how both left and right hand side would equal X. The procedure we usually use here is to say that if E is the identity element, then X star A would be equal to X, in which case A would be equal to something. Whatever we get is a candidate for the identity. That candidate wins the election as the identity if I can also prove that the order equality holds. So let's check that out. So I solve X star E equals X to find a candidate for E. Now E would be the identity if X star E equals X, and that happens if and only if X plus E minus 1 equals X. Remember our definition of X star Y, X plus Y minus 1. And solving this equation, I arrive at E minus 1 equals 0, and that means E is 1. So E equals 1 is not the identity yet, it is a candidate for the identity. You would observe that I'm using an identity and I'm using the identity. As a matter of fact, the identity in a set under the operation star is unique, and I will need you to try a proof of that. Suppose there are two identities, E1 and E2. Prove that E1 equals E2. Again, I will leave that as a simple exercise for serious students. And for my current students, remind me in class, let's look at that proof. Okay, let's continue this. To confirm that E equals 1 is indeed the identity element, we have to verify that equation 2 also holds. E star X equals 1 star X, and that equals 1 plus X minus 1 by the definition of our operation star, and that equals X. So we just prove that E star X equals X. What does that mean? We can now conclude that E equals 1 is the identity element in Z with respect to the operation star. Once more, the phrase with respect to is very important. So 1 is the identity with respect to star. So when I change the definition of star on certain sets, I would expect you to be able to verify if there is an identity using the procedure which I have just outlined in this little example. Okay, let's conclude section 1.4 with subsection 1.4.5, right inverse, left inverse, and inverse. Once more, let star be a binary operation on a non-empty set A, and let E be an identity element of A under the operation star, and let A be an element in A. Number 1, if I can find an element B in A such that A star B equals E, observe that I have A star B equals E, and B is on the right of the binary operation star, and E is the identity element. So if I take A and star it with B and I get the identity element, then this B is said to be a right inverse of the element A. On the other hand, if I put B to the left of the binary operation star, and that gives me E, the identity, then B is said to be a left inverse of A. You can already tell where I'm going. If the left inverse equals the right inverse, then we say that A is invertible. A has an inverse. A inverse exists, and the inverse of A would be B. Let's check that out with an example. Define the binary operation star on the set of integers by x star y equals x plus y minus 1 for every xy in Z. We can say this particular example is our l'enfant chéri, the beloved child in binary operations, because we have used it from the start of the lecture till now. Now, we know that the identity in this operation is 1. So let A be an element in Z. We want to find a left inverse and a right inverse of A, and we want to verify if A is invertible, i.e., does A inverse exist? Let's start with the left inverse. I want to find an integer B such that B star A equals E. This is how we proceed. I say, but B star A equals E if and only if. I'm not yet saying that such a B exists. I'm just saying that if B star A equals E, then that would only be possible if and only if. That is the whole reasoning behind using if and only if. We are not yet assuming that B exists. We are saying if it did, what would that look like? So B star A equals E if and only if. By the definition of B star A, we have B plus A minus 1 equals 1 because our identity E is 1. Solving for B, I get negative A plus 2. So B actually comes out to be an integer. Remember, we were looking for B, which has to be in Z. So two things. Looking for B, and the B has to be in Z. Did we find a B? Yes. Is the B in Z? Yes. Why? Because the sum of two integers is an integer. So we have successfully found an integer B which equals negative A plus 2. And this is the left inverse of A. Right inverse. We want to find a C. Let's call it something different from B. We want to find a C in Z such that A star C equals E. See it on the right hand side. But this happens if and only if, by the definition of the operation star and the fact that the identity is 1, A plus C minus 1 equals 1. And solving for C, we get C equals negative A plus 2. Interesting. So we have successfully found an integer C which equals negative A plus 2, which is an element in Z. And so C is a right inverse of A. Let's put together what we have so far. We have B equals negative A plus 2, the left inverse, and C equals negative A plus 2, the right inverse. The left inverse equals the right inverse, and therefore we conclude that A is invertible and the inverse of A is negative A plus 2. We will use this symbol to represent the inverse of A. It does not necessarily mean that A raised to the power negative 1 equals 1 over A. This is something you will get used to in abstract algebra. Another example. Define the operation star on the set of integers by x star y equals x plus xy plus y minus 2 for every xy in Z. Observe that this is well defined because the sum of two integers is an integer, the product of two integers is an integer, so this star is a well-defined binary operation on the set Z. I want you to verify commutativity, associativity. Check if there is an identity element in Z under the operation star. Pick an arbitrary element A in Z. Does A inverse exist? I leave all of these as simple exercises for serious students. Go ahead and play with this, and for my current students, we would solve something very similar to this in class. Thank you, and God bless you.